Hi, welcome to VadaTech channel. I'm Constantine, I'm an engineer, sales and managing director at VadaTech Asia Pacific Research Center. Today I'm going to introduce VadaTech FMC239, including two synchronized ADRV9009 from Analog Devices. In this video, I will provide details about the hardware, the possible applications, and demonstrate the FMC239 synchronization first between two transmitting channels from the two different onboard chips, and then between two receiving channels from the two different onboard chips. The FMC stands for FPGA Mezzanine Card, which is an open standard from VIDA organization. For info, VadaTech is a member of the FMC Alliance, and the FMC239 is a high pin count FMC fully compliant with VITA 57.1 standard. So on this block diagram of the FMC239, we can see the dual ADRV9009. Each chip features dual channel transmitters and receivers with integrated synthesizer and digital signal processing functions. Each complete RX and TX subsystem includes DC offset correction, quadrature error correction, and programmable digital filters. The transceivers also provide automatic gain control and flexible external gain control modes, allowing flexibility in setting the system level gain dynamically. The FMC239 operates within the 75 MHz to 6 GHz frequency range, covering most licensed and unlicensed bands. The clocking is via the front panel or internal clock, and the FMC239 reference design include actually two configurations for the LMK PLL. In free running, the LMK PLL uses the onboard VCXO as a reference clock. And in the second configuration, the LMK PLL uses an external reference clock coming from the FMC239 front panel clock in or from the FMC connector clock 2 bidirectional as reference to the PLL. Multiple profiles generated with the Analog Devices profile configuration wizard are also delivered in the FMC239 board support package based on the clock ordering options selected with your product. The most important is the reference design implements already the control of the LMK sync pin when multi-board synchronization is required. So who should be interested in such a product? Well, you should if, for example, you're working on a telecom TDD base station with simultaneous support of 2G, 3G, 4G, and 5G, or TDD antenna systems, or massive MIMO, or in military applications such as phased array radar, with support of both wideband and narrowband applications in Milcom and SIGINT, or also the implementation of fast frequency hopping for safer EW systems. That's for the application side. So why synchronization now? Well, first let's summarize that the overall phase synchronization is determined by a number of factors, including the board level clock routing, the on-chip reference path routing, the PLL and LO divider path, and the RF and antenna path. So in a beamforming, MIMO, and other applications listed previously, a system-level antenna calibration is generally performed to equalize the sum of these paths between all channels. This can be very complex and time-consuming if the phase difference across channels is unpredictable over each system reboot. So the goal of this ADRV9009 transceiver mechanism developed by ADI, and especially its phase synchronization as shown on the FMC239, are to reduce the complexity of the antenna calibration by initializing to a more constant startup condition with a deterministic PLL phase and LO divider state, to reduce the temperature dependence of the system phase synchronization and allow the antenna calibration to run less frequently during operation. In other words, the phase between each device is aligned within a few degrees at startup so that the phasing between the device is considered fixed and can be repeated and can be taken into account at system level. Let's now introduce the setup and results of our FMC239 dual ADRV9009 synchronization. We use the RTO1044 oscilloscope from Rod & Schwartz to visualize the transmitter's output. The SMB100A signal generator is used as a source for the receivers. Our module is powered, cooled, and managed in the VT812-2U rack mount chassis. The 100 MHz clock source is generated by the AMC005 GPS module. Finally, the FMC239 is installed on a Zinc UltraScale Plus FPGA carrier. Note that VadaTech support both TCA, PCIe, and VPX FPGA carrier. In this example, in this system, we used TCA structure. So based on the block diagram for the first test, we're going to connect the external 100 MHz reference clock to the FMC239 front panel clock input and test the TX1/0 and TX1/1, respectively from the ADRV9009/0 and /1 of the FMC239. The LO for info is set at 200 MHz here. So we generate a sine wave on both the ADRVs TX at the frequency of LO minus 20 MHz. And then we measure the delay between the two outputs on the RTO1044 oscilloscope. As a result, here we observe a standard deviation of 12 picoseconds with average delay of 42 picoseconds between the outputs. That represents a delay of 2.7 degrees and a standard deviation inferior to 1 degree at this frequency. In the second test, we still have the external 100 MHz as a reference for the FMC239, and we connect one minus 15 dBm sine wave of 199.99 MHz at the input of the RX1/0 and RX1/1 from the two different ADRV9009s. We perform a snapshot acquisition and download the data, then display on a graph to measure the phase difference between the two inputs synchronized. A set of command lines allow easy data acquisition from the FPGA Zinc UltraScale Plus, and as a result, we observe a phase shift within 2 degrees between the two inputs over time and over system reboot. So for more details about the FMC239 and a selection of the FPGA carrier card, rack mount solution, and other I/O or timing cards, please contact VadaTech Sales. If you like this video, please like it and share it, and we look forward to seeing you again on VadaTech channel.